degree n, an equation with degree n, it will have n number of distinct roots. So that's the fundamental theorem of arithmetic, and the n roots are given by this formula. So this formula you can use to find the n roots. I have one example here. I want to solve the equation Zn equals 1. For real numbers there is only one solution, only one, but in complex numbers we will have n solutions to this equation because it's a degree n equation. So A is 1 cos 0 plus I sin 0. I'm using radians here. If you want, you can change this formula and change 2 pi into 360 degrees and get your answers in degrees. If you want to use this as 2 pi is 360 degrees, then you will have theta plus 360k if you want to use degrees. I'm using radians, so A is equal to 1 cos 0 plus I sin 0, and I want to find therefore the nth root. So the nth root, Z is equal to the nth root of the modulus, which is nth root of 1 cos. I plug my numbers into the formula. If you have your formula, it's just a matter of substituting and then writing your n roots, looping through the k values. K goes from 0 to n minus 1, and these are the n roots of unity. For example, if my n is 3, so I'm solving z cube equals 1 equation, z cube equals 1. So if I solve z cube equals 1, I will get 3 solutions for them. Obviously 1 is one of the solutions, but there are 2 other solutions. There is one real number solution if you want to think of this as a real number as well. But there will be also 2 complex number solutions given by this formula, cos 2 pi by 3 and I sin 2 pi by 3 and 4 pi by 3 for that. So those are the 3 solutions solving an equation. So this method is much easier than if you were working with rectangular Cartesian coordinates and trying to find the third root of a complex number. So this polar representation helps us quickly to find roots of complex numbers. So that brings us to the end of the complex number discussion. We want to quickly look at another topic, polynomials in a field. Let me define what a field is first. Field is a set where we can do our basic operations, where we can add and subtract and multiply and divide. So examples of fields that we have are of course the rational numbers. I can add to any rational number, subtract, multiply, divide. Of course they are subject to not being divided by 0. Same with the real numbers and complex numbers. And also during this course of lectures we also found this class, congruence classes, P, where congruence modulo P is a prime. If P is a prime, then I can add congruence classes, I can divide, subtract congruence classes, I can multiply congruence classes, and I can also divide, meaning find the inverses, provided P is a prime. So ZP also becomes a field because I can define my 4 operations on it. The only distinction with that is that it is the only finite field with its note that ZP is the only finite field with P is the only finite field with its cardinality equal to P. The other 3 fields we are looking at are all infinite sets. Only this is the finite set. So what we want to define is polynomials in this field. So you're familiar with polynomials, and polynomial looks of degree n looks like an xn plus an minus 1, xn minus 1 and so on. So that's what a polynomial looks like. And these coefficients of the polynomial must belong to the field. So if it's a real number, then if it's a real number polynomial, then they have to be real numbers. If it's complex, then they can be complex numbers. And x is a variable on that, defined on that field, whatever field we are looking at. So what do we do with polynomials? Of course, the same thing that we have been doing throughout. If you have polynomials, we'll add them, subtract them, multiply them, divide them. That's what we do. That's what we have done throughout this course. We define something, and once we have something defined, we can then see the operations we do on them. We can add, subtract, divide, multiply, whatever operations that we can do. So all throughout this course, that's the key area. What is the algebra? Algebra essentially is these operations that you can do on statements, sets, congruence classes, numbers, functions, polynomials. Now, whatever you define, we want to do the algebra. So anyway, we can also solve equations. That was a big part of this course, solving various kinds of equations. And we can also solve polynomial equations, and the solution of a polynomial equation can be a C in that field, and it must satisfy the equation and you can solve it. So let's look at an example. So I'm not going to look at addition, subtraction, multiplication, division. Those are things you have done many times and you should be comfortable with that. I'm just looking at only solving a polynomial equation in the field Z5, and let's see how to solve this polynomial equation. I can rewrite this using the properties I learned for congruence classes, break it down and write it like this. I could have also written this as a congruence equation, equation, non-linear congruence equation, and solved it, but this is easier. Now I can reduce these things. 36 is equal to 1 because it's 35 plus 1, and x to the 6 is equal to x square using Fermat's theorem, because Fermat's theorem, if you remember, it said that a to the p minus 1 is equivalent to 1. So x4 is 1, so x6 should be x square. And if you plug all that in now, you get that becomes reduces to x square minus x square plus x plus 2 is 0. Therefore, by inspection, you can see these cancel. By inspection, you can see that x will be equal to 3. That's what adds to 0, because we are in modulo 5. So x is equal to 3, and of course if you want, you can substitute 3 into the equation and check that that is congruent modulo 5 to 0, and that's your answer. The topic we are going to discuss in this series of video lectures is Introduction to Graph Theory, or sometimes called maps. So that is, if you want to say find your way from Toronto to Kingston, and there might be many different routes you can travel on, and the idea here is to try and find the most cost-effective way, the most efficient way of finding your way from, say, Toronto to Kingston. And in doing that, you can either minimize the time. Maybe if you take the 401, you will go faster, you can minimize the time. Or you can minimize the distance. Maybe if you take Highway 7 or some other route, you might minimize distance, or you might want to optimize some other issue. So whatever way is that graph theory allows us and helps us to find the optimum route, optimum path from one point to the other. And that's widely used if you have any networking problem, whether it's in the computers or logistics in transporting goods. You need to find the optimum route, the best path, the best possible way of getting there, optimizing whatever criteria you have to. So there are some definitions you need to be familiar with. And what is a graph? A map or a graph is a collection of vertices and edges. So that means you are on some route, and vertices are these endpoints, edges are the connectors that connect vertices. So here is an example of a graph. I have 5 vertices and then I have many edges in this example. So 1, 2, 3, 4, 5, 6, 7, 8 edges in this graph here. So I can have that many edges and vertices. So if a vertex U is connected to a vertex directly by an edge, then they are called adjacent. So you can see that 1 and 4 are adjacent, but 1 and 3 are not adjacent. There is no direct path from 1 to 3. I can, if they are connected, I can go from 1 to 5 to 3 or 1 to 4 to 3, but 1 and 3 are not adjacent in this diagram. But 1 and 4, 1 and 4, 1 and 2, 1 and 5 are adjacent. A walk is a sequence of connected edges. So that means I can go for a walk. If I just start at 1 and go somewhere, I will go for a walk. As long as it's a sequence of connected edges, I can go on a walk from 1 to 3. I can go 1, 5, 3 or 1, 2, 3 or 1, 4, 5, 1, 2, 3. I can go any which way from 1 to 3 in a walk. As long as they are connected, I can go 1, 4, 5, 1, 2, 3. That would be a long walk, but I can still do it. The next definition is if all the edges are unique, then the walk is called a path. That means you can't revisit an edge that you used already. So if I want to go from 1 to 3, I can go 1, 4, 5, back to 1, 2, 3. That would still not walk on one of the edges I have walked on. But I can't revisit an edge if I'm wanting a path. So I can still do a path, which is a special walk. A closed path is a cycle. So I can, for example, I can go from 1 to 2 using or 1 to 1, then I will go on a cycle. So I'll go from 1, 5 to 1. If I did that walk, then it's a closed path. I'm not using an edge again, and that would be a cycle. So for a cycle, I'll start at 1 and come back to 1. That's what a cycle is. But I cannot use an edge twice because it has to be a closed path, and that becomes a cycle. A connected graph, of course, is when you can go from one edge to another, any other edge, any other vertex from one vertex to any other vertex in your graph, then it's a connected. So this is a connected graph. I can start from any one vertex and get to any other vertex. So all the vertices are connected. So I can